Alright, so I'll be solving question 763, partition labels. You're given a string S. We want to partition a string into as many parts as possible so that each letter appears in at most one part. For example, if our string was ABABCC, this can be partitioned into ABABCC, but partitions such as ABABCC or ABABCC are invalid. Note that the partition is done so that after concatenating all the parts in order, the resultant string should be S. Return a list of integers representing the size of these parts. Okay, the first thing that I always like to do is kind of rephrase the question into my own words. So it's saying that we're given a string. For example, let's say it's this string right here. And we want to split it up into substrings, because this right here means substrings, such that every substring contains characters that don't exist in other partitions, right? So for instance, since A exists in this partition, all other A's must also exist inside this partition. Same with B. And since we're making as many partitions as possible, we want to ask ourselves, like, when can we end a partition, right? And the answer is relatively interesting. So the idea is we can do it greedily. And the reason we could do it greedily is because we know that because all unique letters must be inside of the same partition, we have to extend out from the first instance of that character all the way to the last instance of that character, right? So in this example, if we start at A, we know all other A's must be together, so we can extend out to this other A. But we can't just stop there, because inside, between the A's, we have a B. And because all B's must be together, what happens is we have to extend out to the last B. So we extend all the way out here, right? So now we have A, B, A, B. At this point, no other characters were introduced inside the sandwich, and we can stop there. And then we start at C, then we go out to the last C, which is right there. An interesting fact is, let's say we had all unique characters, right? What do we do in that case? Well, it's actually pretty simple. So if all characters exist once, then each letter can be its own partition. And the reason is because we know that we don't have to extend out anywhere, right? All right, so our objective is to make the most partitions, so we can do this greedily. So let's assume that we have an empty partition. Let's do it on this example here. We have an empty partition, then we add the first letter. Because each letter can only exist in one part, we know that the substring that contains the first character must extend out to the index of the last instance of this character, right? So this A starts here and it ends all the way here, right? Otherwise, the same character will appear in a different partition, which kind of breaks the rule that we're trying to save here. All right, and for every character that is sandwiched between the first and last instance of another character inside this substring, we can scan for the last instance of that character. So for B, the last instance of B ends right here, which is earlier than the A. And then for C, this ends right here, which is also earlier than the A. And at this point, there is no more unique characters that are sandwiched in between, right? So for that reason, we can safely assume that this is a partition. It contains ABC, and there is no more ABCs in the rest of the partition. When we start a new partition, we assume it's empty, so we start at the next letter. So D, we have to extend all the way out to the last D. Then for E, since it's sandwiched in between the D's, we extend all the way out to this E right here, and this is longer than the length of the last D, or the last instance of the last D. So for that reason, the end value we can update to be this index right here. Similar for f, this is the only f in the string, so we don't have to worry about it. Same for this g. So this right here, starting from the d to the e, has to be a substring. And from here, h has to extend out to this h, I has to extend out to this I, j has to extend out to this j, at which point we're at the last character, so we know that this whole thing right here has to be a partition. And that's why we output 9, 7, 8, because we have these 3 partitions. All right, so I think what we learned there was that the partition end is the last occurrence of any character that we've seen so far inside that partition, right? The data structure that makes the most sense in that case would be a dictionary, because we can keep track of 2 things, right? The character itself and the index of the last instance of that character. And the reason that's useful is because we can just jump from the first index and scan through all the characters from that index to the last index, and then we can use the dictionary to kind of access every single character in between, right? And since this is hard to do dynamically on the spot, like if I started with this A, like I have no clue where the last A is, it would make a lot of sense to do an initial loop that maps each character to the last index where it's found, right? So with this, we can loop from the start of the string, and then from the first index, we can check the map to see how far we have to extend out. And while this index is less than the max end of a character, so what does max end even mean? It means that, let's say we had an A, and sandwiched in between the A's is a B, but that B had a later end than that last A, right? That becomes the max end. We have to extend out to the last instance of every character that is sandwiched in between. Once we reach the max end without incident, which means, oh, no more characters, and after this, we can store the length of the substring and then create a new part from the character right after, right? So let's do that. So as I mentioned, we do want to create a map mapping characters to the last index. So we'll use last seen as a map, and we can do character to index, so we should enumerate for index character and enumerate s. We can populate the map with last seen at char is equal to index, and the reason this works is because it will update index if we find one later on, so this will always map character to the last index. And then our output is going to be a string, no, it's going to be a map of integers, so a list of integers. So that's going to be our result. And then since we want to keep track of 2 things, which is the start and the end, we should make variables for that. And the reason we need start and end is because eventually we do need to keep track of the size of the partition. So we can do start partition is equal to 0, end partition is also equal to 0. Cool. So what we have so far is map character to its last index, and then we have our result array as well as our pointers for the partition. Cool. All right. Now what we do is we loop through string again, so s, and we have to do it using enumerate because we want the index as well as character. For index char in enumerate S, what we're gonna do is we're gonna set end partition is equal to the maximum of end partition or the map at char. So last seen at char. And we know that since we initialized it as 0, this will always be updated accordingly, right? It won't be like doing any wrong math here. And then we check if the index value is equal to end partition. What this will do is tell us that we finished looking through all the characters between the first instance of the first character and the last instance of the first character, and we mapped all the way out to the last instance of any character inside that section, and our partition is done. So we can append to our result res.append, and then we have length of the substring, which is end partition minus start partition plus 1, because r minus l plus 1 is the length of the substring. And then we'll restart the partitions using the next unique character. So start partition is equal to end partition, because it's not inclusive, plus 1. And then at this point, I think we're good. So let's return ans. Before I run it, I do want to do a dry run. So a dry run is essentially during an interview, before you say, okay, I'm done, you'll be like, okay, let me use a test case that I came up with. In this case, I'll use example 2, and I'll go through the logic that I written down, and I'll explain to you why it's correct, right? So last seen for this one, there is 1, 2, 3, there's 10 characters. Index 0, index 9 is this one, and it's index 8, I'm assuming. So we'll have E map to 8, C map to 9, B map to 0, 1, 2, 3, 4, 5, 6, I believe. And then D is just 7. Oops, B is 6, D is 7. Cool, that should be all the characters. And then this is done, result is empty, start is at 0, end is at 0. So for every character in S, end is the maximum of last seen at the first character, which is E, so that's going to be 8. And then this doesn't turn true, so we go to the next character, which is C. We get end partition becomes 9, and then we loop here. It's also 9. I's index is still not 9, so we don't worry about that. Same thing for B, same thing for D. Once we get to this E, I or index is gonna be 8, which is not end partition. So we loop to the next iteration, which is going to be index 9. And this is equal to end partition, which means we just append 9 minus 0 plus 1, which is 10. And start partition will be at 10. And if we return, oh, it's res, I believe this should work. Let's see. Partition, what a typo. Partition. Okay. Oh my god, partition. Can't spell. It's okay. It's okay. There we go. All right. Time and space complexity. We do loop through it twice. which is O of n. Since the constraint is that it's all lowercase letters, technically the map is constrained to O of 1. But it's going to be time complexity O of 2n, which is O of n, space complexity O of 1, because it's kind of bounded by the lowercase English letters. Cool. Thank you for listening.